When solving this problem, the first thing you might think is that it's incredibly complicated and really intimidating. But I want to show you that by identifying your nodes, this problem that looks really hard might end up being one that's not as difficult. A former student of mine once told me that this circuit looks like a Dorito. So since then, I've called this problem the Dorito problem. And so in order to solve the Dorito problem, let's first identify our nodes. I'm going to use orange to label my nodes because it's a Dorito. We're going nacho cheese Dorito here. So I'm going to start by labeling the node closest to the power source as node 1, and then I'm going to keep along my path labeling each one as I approach it. Thinking about the circuit as I keep labeling each node, seeing where I'm having different paths form, and seeing where things might be in series. Now that I have each of my nodes labeled, it will be easier to understand the problem if I redraw the circuit. I always start with the voltage source, and then I go to node 1. At node 1, I see that there are 2 paths in order to get to node 2. Knowing that there are 2 paths, I'll draw that on my new circuit. I'll address the first path by going from node 1 to node 2. I go across R1, and then I can go from node 1 to node 2 by crossing R2. Now, if I'm at node 2, I can go to node 4 by taking 2 different paths as well. So I'll label that on my new circuit. I'll take the first path that passes over R5, takes a pit stop at node 3, passes through R7, and then gets to node 4. So I have R5, take a pit stop at node 3, then go to R7, and then I reach node 4. And then my other path goes through R6 and then reaches node 4. Then finally at node 4, I can see again I have 2 paths in order to get to node 5. My 2 paths are labeled on my new circuit diagram. I can go across R3 to get to node 5, or I can go across R4 to get to node 5. Then I see that node 5 reaches the ground of my power source, and I can close out my new circuit. Now you can see that this circuit is a lot less intimidating than the Dorito circuit that I have above. Once I have my circuit redrawn, I can label my known information. I know that the voltage source is 21 volts, R1 is 11 ohms, R2 is 10 ohms, R3 is 29 ohms, R4 is 75 ohms, R5 is 132 ohms, R6 is 32 ohms, and R7 is 12 ohms. Knowing that I'm trying to find the power delivered by the voltage source, I know that I can take a few routes to find that information. I know my power equation is current times voltage, or current squared times resistance, or voltage squared over resistance. My known information right now is I have voltage, and I have all the individual resistor values. Knowing that I have that information, I can look at my power equations and identify the one that contains voltage and resistance to be the easiest one for me to use to find power. So in order to use that equation, I know that my voltage in this equation is my voltage source of 21 volts, but my resistance has to be the equivalent resistance. I can see that there are 3 parallel portions of my circuit. I can label each one A, B, and C and find their individual equivalent resistances. And then once I find their equivalent resistances, I know that A, B, and C together are in series with one another. So let's take a second and solve our intermediate stages. The Req of A is going to be 1 over 11 ohms plus 1 over 10 ohms, which equals 5.238 ohms. Then I have Req of B. Before I write the formula for that, let's talk about what's going on here. I see that R5 and R7 are in series with each other, and those are in parallel with R6. So I can write that all in one form by just saying R5, which is 132 ohms, plus R7, which is 12 ohms, in the denominator of this portion of my parallel component in the equation. Then I have the 1 over the 32 ohms for that R6 resistor. This gives me 28.182 ohms. And then finally, I can find Req of part C, which is a simple 2 resistors in parallel with one another. 1 over 29 ohms and 1 over 75 ohms, which is 20.913 ohms. Now that I have the equivalent resistance for each parallel part of that circuit, I can redraw my circuit and more easily see how these three parts combine in series. REQA is 5.238 ohms, REQB is 26.182 ohms, and REQC is 20.913 ohms. Each one of these is in series with one another, and so I can now find the total equivalent resistance by adding them together. The equivalent resistance is 52.333 ohms. We can redraw that circuit with one resistor of 52.333 ohms and 21 volts as its voltage source. Now, seeing it as a simplified circuit, we can apply the power equation V squared over R, which would be 21 volts squared over 52.333 ohms. Our power is calculated to be 8.427 watts, which is answer I on our answer choices.